Hello, T-Rex math students. Today we're going to take a look at learning target number 1, predicting the ways that stretching or shrinking a figure will affect side lengths, angle measures, perimeters, and areas. And you're going to start to develop a working definition of what the word similar means. Since these are the current learning targets, you'll want to take a look at the corresponding IXL starting with 7th grade AA14 and Geometry P3. Since at this point you've finished the task board, we want to start to look at the patterns we've noticed. So if you look at the image that we started with, the original drawing, you see a picture of a mystery or super sleuth, they call it. And when you enlarge it 1.5 times its size, here's what it would look like. So with the rubber band, it allows you to copy the figure into a bigger image like you did in the task board. Whenever we have an original drawing, like the one I just pointed out right here, okay, this would be our original drawing. Whenever we enlarge it or shrink it, that has a name and we call it the copied image, which you would have written down in your vocabulary chart. This figure right here, we shrunk it, but it is also a copied image. It's not the original. It's either shrunken down or enlarged, and that's why it's called an image. The drawing you made with the 2 rubber band stretcher would be considered an image. So thinking back to that rubber band stretcher, when you had your knot follow along the edge of the picture, you got a line that was about twice the size of the original. Think about you had 2 rubber bands knotted together, and when you used the knot of the rubber band, because there was 2 rubber bands, your image on one side length was twice as long. So we're going to start to investigate why that is. Why does the side length double with 2 rubber bands? We're also going to start to look at what's called corresponding angles. So the angles I marked in red right there are corresponding. They're in the same position, but they are in different figures. Okay, so we have a triangle right here, and we have a larger triangle right here, and those corresponding angles are in the same position on 2 different triangles. We can also look at this angle up here, which corresponds to this angle of the smaller triangle. And finally, we have this angle right over here that overlaps and corresponds to the other triangle's angle as well. Think about if we would have connected 3 rubber bands on the stretcher. And if we use the first knot, we would get an image that is 3 times as large. Okay, so if, for example, if we look here at the path of the knot, again in the triangle, let's say that that is 1 centimeter. If we had a rubber band stretcher that was 3 rubber bands long, and we use that knot along this path, if we look at the corresponding image and its path, we could say that that image is 3 times the length. Or in other words, if we were thinking in terms of centimeters, if the original is 1 centimeter, the image that's copied would be 3 centimeters. Even though we used 3 rubber bands in that example, if we look at those angles again, this angle in the bottom right of the larger triangle corresponds to this angle. Okay, do you think they are the same measure? This angle up here corresponds to this top angle down here, and this angle in the corner, they overlap in both images and the original. So we're going to start to see, okay, if we measured those angles, would the corresponding angles be equal? So at the beginning of the video, I mentioned that we're going to be looking at a working definition of the word similar. And when you study similar figures, you're going to start to notice that you are comparing both their sides and the angles, like what we just did previously. We're going to start to look at the corresponding sides and the corresponding angles. So in the case of the triangles below, we could say that angle B corresponds with angle E. So angle B corresponds to angle E. Do they look like they are the same measurement? Okay, that's what we're going to figure out. Angle A corresponds to angle D. Same measure. And angle F corresponds to angle C. Does that look like they're the same measure? Likewise, we're going to start to look at the sides of the triangles further. So side AC corresponds to DF. It's in the same position on an image of the original. AB corresponds to DE. It's the same position, but on the original and the image of the triangle. And finally, BC corresponds to EF. Same position on both the original and the copied image. What do you notice happened to the length of the sides as the image was enlarged? What was the ratio or the factor that the original to the image gets enlarged by? What would you estimate there? In other words, if I look at my original figure, the original figure being the first triangle, and I compare it to the image that's copied, how many times larger do the side lengths look? Are they 1 time larger? So if we go AB to DE, how many times larger is that side length of the copied image versus the original? How many times larger then would line segment DF be compared to AC? Is it double, triple? And then finally, how many times longer is line segment EF than BC? You'll notice they're consistently the same amount of times larger. So right now we're just estimating how much that might be. Is it 1 times larger, 1.5 times larger, 2 times larger, 3 times larger, or so on? At this point in time, make sure you go and get your math notebook. There are a few key ideas that we need to record from what you just watched. Number 1, I'd like you to create a working definition for the word similar. What do you think it means for 2 figures to be similar? Pause the video and write your ideas down in your notebook. Number 2, what did we talk about in terms of original picture versus the copied image? What is the difference? Go ahead and draw an original image like the one I drew. And then almost imagine you're going to take a picture of that original and zoom in. Now, rather than it being called an original, because you enlarged it by about 2 times the size, that would be called an image. Draw that in your notebook. Third, corresponding sides. So pick an image like I did before. Let's take and go here with a rectangle. So if I were to label this side as side AB, and then I were to take that same type of rectangle and take that original and copy it as an image, let's say almost twice the size, just estimating here. And let's say this were side length DE. So I could say then that AB corresponds to DE. And I could even kind of click this over, and yeah, it's about double, maybe 1.5 times longer on each side. So those sides would correspond. And then if I went ahead and looked at the top side length right here, I would say that that green side length, where I put an X right here, corresponds to that top side length. And so if side lengths correspond, then angles would correspond as well. So if we were to say build a triangle and then duplicate the triangle, enlarge it, let's say double the size, okay, and just like the sides correspond, so this left side would correspond with this left side, we could also say that the angles correspond. So if you look at the top acute angle, that would correspond to this angle as well. So if this is angle A and this is angle B, those are corresponding angles. They're in the same position on the original and the image. This angle, let's say it's a right angle, corresponds to this angle. Let's call it angle C and angle D. And then finally, if we have the bottom right acute angle, let's call it E. Angle E would correspond to angle F, same position, but on the original and the image. Do you think those are the same measure? Predict what you think. Do you think those angles are the same measure if we were to take an angle ruler or a protractor and measure them? Likewise, predict how many times greater is the image's side length compared to the original. Go ahead and write down your prediction. Remember that this triangle is the original and the enlarged triangle is the image.